Find an equation of the line where the two planes intersect. So, to get us started here, let's simply think about what we're given. Two planes. So, the first plane is defined as minus x plus 2y minus 4z is equal to 1. So, we can identify this plane's normal vector, we'll call it vector n sub 1, by looking at the coefficients of the variables. So we can see that this plane has the normal vector with the components -1, 2, -4. And we're also given plane number 2, x plus y plus z equals 0. And again, we can define this plane's normal vector, we'll call it vector n sub 2, by looking at the variable's coefficients. So the normal vector to this plane is the vector with the components 1, 1, 1. So we'll need these normal vectors when we find the vector that is parallel to the line. So let's really quick think about what is our goal? What do we want to find here? We want the line of intersection. So we're looking for that vector valued equation, vector r of t, being equal to vector r naught plus that arbitrary parameter t times vector v. And this is such that vector r naught is the position vector. So that means that it's the vector defined by the directed line segment from the origin to some point p naught. And this vector v is a vector parallel to the line. So, in order to find this line of intersection, we need to find a point on the line and on these two planes, and we also need to find a vector that is parallel to the line. So here we go. Step number 1. Let's find a point P naught. Now, I want you to keep in mind that there's multiple ways to go about finding this point P naught. My favorite method is to find the point where these two planes intersect one of the coordinate planes. So let's choose one of the coordinate planes. We're going to find P naught where the planes intersect. Let's do the xy plane. So if we're looking at the xy plane, we know that this is defined as z is equal to 0. So in order to find this point, we're going to let z be equal to 0, and then we'll solve for x and y. So we let z be equal 0, and we solve the resulting system for x and y. So thinking about our first plane, plane number 1, this becomes minus x plus 2y minus 4 times 0 equals 1. And this leaves us with the equation minus x plus 2y equals 1. Now, plane number 2 becomes x plus y plus 0 equals 1. Leaving us with the equation x plus y equals 1. Oops, shame on me. It's not equal to 1. It's equal to 0. Minus 1 on my test. Phew, at least we caught it. Now, the important thing here is that we're left with a system of two equations. So we can now solve the resulting system for x and y. And let's go ahead and give ourselves plenty of room. So here we go. And how you solve is entirely up to you. Now I'm noticing here that this first equation has a negative x, but the second equation has a positive x. So what I'm going to do is simply add equation 1 to equation 2 to eliminate the x's. So we're taking equation 1, which again is x, or minus x, plus 2y equals 1, and we're adding this to equation 2. X plus y equals 0. So notice the x's cancel each other right out, leaving us with 3y equals 1. Dividing both sides by 3, we see that y is equal to 1/3. Beautiful. So now we can take this y equals 1/3 and substitute it into either equation to find x. So I'll go ahead and we'll take this and we'll plug it into equation 2. So this is x plus 1/3 equals 0. And so x is equal to -1/3. Hooray! So we can say that therefore the point P0 will have the coordinates. So this is x0, y0, z0. We just found that x is -1/3. We found that y is +1/3, and we let z be 0. And so the position vector, vector r0, again, that is the point from the origin, or excuse me, the vector, the directed line segment from the origin to P0, is going to be the vector with components -1/3, +1/3, 0. So the first part of our solution is ready to go. So now that we have the point P0 and the position vector, we need to go ahead now and find the vector that's parallel to the line. So we want to find vector v. Now, vector v is going to be defined here by the cross product of the two normal vectors. So here we go. We need a little bit more room. I also want, before we start looking at this solution, I want you to note that letting this parallel vector v be defined as the cross product of vector n sub 2 with n sub 1 also works. So there are multiple correct answers, not only for the point that you find, but there's also multiple correct answers for the vector v that you find. And the reason behind this, we know that the cross product of vector n sub 2 and n sub 1 is equivalent to minus the cross product of vector n sub 1 with vector n sub 2. So using any scalar multiple of this vector is going to work. So here we are going to use the cross product vector n1 cross with vector n2. But keep in mind, any scalar multiple will work. So here we go. We are going to let vector v, again, be defined as the cross product of vector n sub 1 with n sub 2. Putting this into our 3 by 3 determinant, we have the row of unit vectors I hat, j hat, k hat. Our second row is -1, 2, -4, and our second row is our third row is 1, 1, 1. So by the definition of the cross product, we are left with 2 times 1 is 2, minus 1 times -4 is -4. I hat minus -1 minus a -4, j hat plus -1 minus 2, k hat. And of course, always be mindful of these negatives. And what are we left with? So we have 2 plus 4 is 6i hat minus a +3, so that's -3 j hat. And then we have a -3 k hat. So therefore, vector v is equal to the vector with the components 6, -3, -3. And I'm noticing here that there's a scalar multiple of 3. So we have 3 times the vector 2, -1, -1. So using this full vector, 6, -3, -3 is fine. That's a correct answer. But you can also use the scalar multiple version for smaller numbers. That's entirely up to you. And why is this okay? Well, these vectors are scalar multiples, so they're parallel. So here, I'm going to go ahead and let my vector v be the smaller vector, 2, -1, -1. And this is fine. This is great. We can use this vector because it's parallel to the vector that we just found. Woohoo! So, depending on which point you find, and depending upon what vector you use, will dictate what your line of intersection will look like. So, multiple correct answers exist here. So, we have everything that we need, though, so let's go ahead and let's find this line of intersection. So, find the line of intersection. So here we go. We have our vector valued function r of t is equal to vector r naught plus an arbitrary parameter t times the parallel vector v. So we have our position vector. That's -1/3, +1/3, 0, plus t times the parallel vector 2, -1, -1. And simplifying this, we are left with the beautiful vector valued equation of the line, -1/3 plus 2t. We have +1/3 minus t. And then we have 0 minus t. And this is a full line, so t can be any real number our little hearts desire. So this is our beautiful final answer. This is one beautiful final answer. Right? This is not exclusive. Another correct way to write this would be a vector valued function r of t is equal to, we could use that same position vector, -1/3, +1/3, 0, plus t times the vector 6, -3, -3. That's also correct, right? Because this vector v is parallel to this vector v. So it's important to keep in mind as you work through these problems that there's not just one correct answer. There's always multiple correct answers. Now, with that in mind, let's make ourselves one little final love note here. So multiple correct forms of the answer exist. And we've seen this with these two forms of the answer above. But even more than that, depending upon how you find P naught, will change this answer as well. So for fun, because math is fun, let's find another point P naught. So let's find P naught, and this will be such that the two given planes intersect. Let's do the YZ plane. So keep in mind, with the YZ plane, we know that that is defined by the equation x is equal to 0. So here, we're going to let x equal 0 and solve the resulting system. So thinking back to those given equations, equation number 1 is now going to be -0 plus 2 times y minus 4z equals 1, which leaves us with 2y minus 4z equals 1. And plane number 2 is going to become 0 plus y plus z equals 0, leaving us with the equation of two variables, y plus z equals 0. So we have a new system of equations with two variables, and we can use this to solve for y and z. How you solve this is up to you. I'm noticing here that the z variables in both equations have opposing signs. So to solve, I'm going to take the second equation and multiply it by 4, and then add this to the first equation to eliminate z. So we now have 4y plus 4z equals 0 plus 2y minus 4z equals 1. And notice here, the z's cancel each other right out, leaving us with 6y equals 1. And dividing both sides by 6, we have y is equal to 1/6. Beautiful. So we can now take this equation, or this y value, and substitute it into either equation to find z. So I'm going to use equation 2. So this is going to be 1/6 plus z equals 0. And so z is equal to -1/6. Beautiful. So we can say that therefore our point, P0, where these two planes intersect the yz plane, is the point with the coordinates x0, y0, z0, where x is 0, y is +1/6, and z is -1/6. And so therefore the position vector r0 is the vector with the components 0, 1/6, -1/6. So if we use this new point with that same vector v defined as the cross product of the normal vector n sub 1 with n sub 2, and we use the smaller version, 2, -1, -1, we'll get a new line. It's still correct, but it'll look different than our original line. And I want to make sure that you can still see that original line. So another correct answer is the vector valued function r of t, where we have the position vector 0, 1/6, -1/6, plus t multiplied by that parallel vector 2, -1, -1. And we could group up our like terms for the beautiful final answer of 2t, 1/6 minus t, -1/6 minus t, where t is any real number our little hearts desire. So this is also a correct answer. And more exist. So we have two possible correct answers here. We have the one that we just found, and we also have this original. Well, we have two original solutions that we just found. So this is really demonstrating to us how multiple correct answers exist here. It's all dependent on how you define your point P0 and how you define that parallel vector V.